two parts to this workshop. One in which I give some specifics about implementing peer instruction and just-in-time teaching. I will not give the rationale. The rationale and the data are in the video which you watched. And in the second part, and during the first part, I'm also going to address some of your outstanding questions, which I have here. And I will also use the second part to get into more detail. And it'll be interactive. So the first thing to do is perhaps to look at these clickers and get it out of the way. We're going to use them as polling devices first, not as a pedagogical device. That will come later, because I want to first demonstrate how they work, and I want to also survey to see where you stand in your attitude towards teaching. There's no on-off button. I'll show you the view that I have on my computer. I have this little window that floats in front of whatever presentation software I use. When I hit this play button, the polling is open. You can press on any button now, and you'll see that number go up. So go ahead, just press a random button on your clicker. If you've pressed once, let's say you press 5, and then you think, oh no, I should have pressed 4, you can press 4, but you don't get to vote twice. The 4 overrides the 5. Okay, so you can press as much as you want. It's the last click that counts. So let's use it for some polling first. 1, peer instruction. I've never heard of it. I heard of it, but I don't really know what it is. I'm quite familiar with it. 3, I heard you speak about it so often I could give your talk. So go ahead, press the button corresponding to whatever you would answer. Everybody, please. So let's see. Well, there's at least one person who has heard me several times. Would you please come forward and give my talk for me? I'm just kidding. But this is a little bit disconcerting, because unless you were in a coma when you watched the video, you should have heard the word peer instruction at least 100 times. So I guess some of you are not that good students. I wonder what you would do if your students didn't do their pre-assigned work. We'll actually get back to this. Oh, before. Okay. Before watching the video. Okay. Okay. But we have about 30% of the audience, which is very good, which is quite familiar with it. So let's go to the next question. Peer instruction, never heard of it. I don't use it in my classes, but I'm open to it. Considering using it in my classes, I've used it in my classes a few times. I use it regularly in my classes. Go ahead. Let's wait another few seconds. Okay, so if all is well, category 1 must be gone now, because you've heard me pronounce the word peer instruction. There's still one person who has never heard that word. But this is really interesting. We have a couple of people who are quite expert already, about 12% here. Broad distribution. So that means I hope we can learn from each other, and I from you too. So we'll have, but I have my work cut out for me, because I want to, towards the end of this workshop, I want you all to be much more towards the left side of this graph. So let's start by doing a little reflective exercise, because I'm going to be talking about teaching, but the really important part is the learning, not the teaching. Right? You can teach as much as you want. What matters is how much is learned. And if you watch the video, my Confessions of a Converted Lecturer, you've seen the data that showed that in spite of being a well-regarded teacher, getting excellent end-of-semester evaluations, and having students capable of solving some quite complicated homework problems, my students were not even learning what they should have learned in week 2. Totally shocking. Okay, so here I was, award-winning teacher, students being able to solve homework problems straight out of the textbook, yet the concept of force, which is covered in week 2 in an introductory physics course, they had no consistent model of it. In fact, a gorilla randomly choosing choices on the force concept inventory would do better than some of the students at Harvard in my intro physics class, at the end of my intro physics class. So I want you to reflect a little bit about learning, because we're often unaware of how we learn. So I want you to think, I want you to take all a little piece of paper, And this is going to remain private information, so you have to be really honest and hide it from your neighbors. This is just for you. But I want you to write down something you are good at, something you know you are good at, you do well, you're proud of it, and you know that other people respect you for it. Ideally, that something should be something that has advanced you in your career, right? It could be communication skills, it could be solving partial differential equations, it could be, analyzing medieval writings, it could be gardening, it could be cooking, something. I don't see how cooking would advance you in your career unless you're a chef, but, who knows? Write it down and then cover it up because it's just, your private information. I will not harvest it. You don't want your neighbor to see it. Be brutally honest. Okay, so now that you have committed to something, cover it up. Nobody needs to see it. But now comes the hard question. How did you become good at whatever it is that you wrote down on that little piece of paper? Where did you develop that skill? What did you do to get better at it? Reflect back on your learning, on your acquiring that skill, and write down in a few words the circumstances that led you to become good at it. Now that's harder, because especially with the things that we're really good at, we tend to completely forget how we got good at it. So reflect on that for a moment. But let's see, the responses that I've collected fall into these categories: trial and error, lectures, practicing, apprenticeship, and then, sort of a catch-all other category. I want you to indicate which of those choices most closely correspond to what you wrote down, how you acquired that skill. So 1, trial and error; 2, lectures; 3, by practicing; 4, by watching a master, right, an apprenticeship and learning from that, rather than inactive. That's the same everywhere. What's also the same everywhere is another very notable thing about this distribution. I don't know if you see it, but look at it again. There's another thing that absolutely stands out. What is that? Lectures. One person selected lectures here, but that's only one out of this audience. And I've done it with audiences up to 1,000. And even then, you only have 1 or 2 people selecting lectures. And how do we teach? This is how we teach. This is how our learning spaces are, including this very room here. In 3 slides, I could give you the history of, the development of learning spaces. It all goes back to before the Greek, actually. In the Middle East, you can see there's an illustration of a palace school in Syria, which dates back to 2400 BC, which has the same arrangement as our learning spaces now, built with just one purpose in mind: focusing the attention of many onto one. And here we are in the 21st century, and we still use that very same approach. This is a picture of me teaching my pre-med course. This was taken BC, by the way, before computers. Right? I'm using an overhead projector there. So you saw this picture in the video, Confessions of a Converted Lecturer, and basically in that video I asked people to consider what is happening there, and what is happening there is really that lectures focus on information transfer. Sometimes, when I ask audience what is happening there, they say sleeping. Of course, that offends me terribly because these are my students. But I recently heard a fantastic quote from the French writer Albert Camus, who said, "Some people talk in their sleep. Lecturers talk while other people are sleeping." I like that one. But not in my class, of course. In my class, they're awake. So lectures focus on information transfer, but education is so much more than information transfer. And if you think about it pragmatically, what is education really? Well, information transfer is part of it, right? Because if you don't transfer information, there can't be any education. But as a learner, you need to do something with that information. You need to make sense of that information. You need to connect it to your own experiences. You need to extract the knowledge out of that information so that you can apply what you've learned into a new context. transfer it to a new context. Not just spew back the information, but if you think of it, so much of our education consists of the instructor delivering information to the students regurgitating it back on the exam. Either facts, or sometimes, you know, the professor solves a problem, students write it down, and then on the exam, the students reproduce the solution that was presented by the instructor. And then you show a student something that they've not seen before, and they say, we've never done a problem like that. Well, if you had done a problem like that, it would no longer be a problem, by definition, right? And the problems that you're going to face later in life, no matter where you're educated, are not going to be the problems that are presented to you in the classroom. So we have to prepare our students for learning to tackle situations they have not yet seen. So the essence of learning is really be able to take what has been taught and apply it into a new context. So, and that's why that second step is so important. Now, the traditional approach to teaching focuses completely on that first step, which is easy, especially now in an information age. Until the Industrial Revolution, there was no other way to transfer the information but to have the professor in front of the classroom deliver the information. But now, the information comes from everywhere. Why reenact the same lectures over and over and over again, especially when the audience sits passively, like you right now, but it won't last very long, I promise you, right? Why not just videotape it and put it in front of people, which is why I had you watch that video. Otherwise, I would have taken the first 1 hour to motivate you for what I'm doing. Okay, so where does this assimilation take place? Where did it take place for you? Where did the aha moments occur? Where did the insights occur? Did they happen when, I'm talking about the time that you were a student. Did it happen when you were sitting in the classroom listening to your instructors taking notes? Maybe some, right? Maybe some of it, but most of it happened outside the classroom. Now, if you think about this completely pragmatically and you ask yourself, which of these two steps is the hardest? I think we would all very quickly agree it's step number 2, not number 1. So it's kind of ironic that we put all of the emphasis on step number 1 and leave the hard part to the students. We should flip this around. Throw the information transfer out of the classroom so that we can focus on the information transfer. But that brings, of course, the big question, how do you move the information transfer out of the classroom? And in this first part of the workshop, I'm going to show you how 2 techniques, peer instruction, which you were introduced to in the video, and just-in-time teaching, which I'm going to introduce today. So just-in-time teaching is something I will introduce today. Okay, so I'm going to do a quick 6 or 7 question survey. Okay, I'm going to flash the question, or statement actually, and I want you to click 1, 2, 3, 4, 5, depending on how strongly you agree or disagree with it. I'll show you the distribution, we go to the next question, show you the distribution and so on, and we'll repeat this at the end of this workshop before I finish, because I want to see what your attitudes are towards learning and teaching and see how it evolves over the course of this classroom. Where's my controller here? Okay. So there we go. The first question is, lecturing is the best way for me to cover all the material I need to cover in my course. If you agree strongly, press 1. If you disagree strongly, 5, or any of the variants in between. So people tend to be towards the left, but there's quite a broad distribution. So there are people on the opposing ends of the spectrum. Okay, so now the next one. Interactive teaching requires significantly more instructor preparation time than a traditional lecture. If you agree, or you think you agree because you might not have done it, then you press 1, press 5. Okay, so let's see. Oh, we're getting more people responding. That's good. So I guess a lot of you have either taught interactively and discovered it takes more time. I'm going to try to tell you that that's not true. Or some of you are worried that it might take more time. So I hope I'm going to be able to give you some resources to prevent that from happening. Okay, so next question. Interactive teaching requires clickers. There we go. Strongly disagree. Good. Well, we'll talk about that later. But yeah, that's one of the things I'm going to show you. It's not the technology that matters, it's the pedagogy that matters. So much investment is being made in technology right now without thinking about the pedagogy. When I started implementing peer instruction, I did not use clickers. There were no clickers. They had not yet been invented. I used the show of hands and scanning cards because I wanted data. I'll show you how you can do it without really having students raise their hands, because that is, not a very effective way. We'll do that later. Okay, next question. I know how to get my students to do their reading before class. Ooh, bimodal distribution here. Okay, this is a very important one, right? Because if we want to move the information transfer out of the classroom, we've got to count on this, right? So we'll be talking about that. That's an important question. Next one. It is difficult to see how to apply interactive teaching techniques in the humanities or social sciences, right? I mean, in physics you have right, wrong, mathematics, and so on. But what about history or a philosophy course? This is the penultimate question. So let's see. There we go. Okay, that's good, because I was going to argue that you can use it in all fields. We'll even do a question that illustrates that. Okay, next one and last one. I'm worried that interactive teaching will negatively affect my end-of-course evaluations. Good. I'm really happy to see. I don't know what 6 is, but I'm really happy. I'm really happy to see that, because there are many audiences where the faculty is incredibly obsessive about the end of semester evaluation and worried that whatever they do will affect their end of semester evaluation. As long as we are slaves to the end of semester evaluation, education is not going to improve. I have discovered that the end of semester evaluation has nothing to do with the amount that is learned. It's more something like charisma or whatever, satisfaction. I could give my students foot massages and my evaluations would probably go up, right? I mean, it's actually quite amazing that the system we've set up, right? I mean, to be an electrician, you need to be certified. To be a nurse, you need to be certified. To be a doctor, you need to pass exams. To be a lawyer, you need to pass the bar exam. To teach kindergarten, you need to have a certification. To teach in higher education, by virtue of the degree that has been conferred upon you, you become a member of the Society of Learned Women and Men, and you know how to educate. What's more, we get to assess our own teaching, right? Because basically we teach and then we set the exam. Can you imagine that in any other human endeavor, right? The electrician who doesn't need to be certified does work and then sort of, examines his own work, right? Rather than being examined by other people. I mean, it would be inconceivable. But that's the system we have in higher education, and which is probably one of the... plus, we use another totally false metric, student satisfaction, to judge how well we've taught. Now, I don't want to minimize student satisfaction. I mean, we don't want to have students leave our universities very dissatisfied. But ultimately, what says whether or not the education has been successful is how much students have learned, which is something that takes a lot longer to evaluate, because you have to see how successful your alumni are, right? Yet, we have built a system that holds itself in place with false metrics. I mean, it's kind of shocking. But I'm happy to see that you're not too worried about your end of semester evaluation, because that is something that is crucial to improve education. Okay, so what I'm going to do in this first part, so the first part is a little bit longer, and then we'll have a 10-minute break to stretch our legs, get some coffee if there's coffee, and so on. And then we'll have a second part. In this first part, I'll give a quick overview of peer instruction and just-in-time teaching. Then I'll talk about implementing them, and I've seeded this with some of the questions you have asked. And then we'll talk about the design and the important parts of the concept test. And at any time, if you have a question, Yesterday people were very lively, so I hope I can get you just as lively today. And if you're skeptical, you should just voice your skepticism here, not just swallow what I'm telling you here. But I won't tell you that much because this is a workshop, not a presentation. So here's a question that one of you asked. I've taken your questions, by the way, and paraphrased them because some of them were quite long, so I've shortened them. But there were a couple of people, and this is true for every workshop I give, who asked, how can I be sure that my students will prepare for class? And a lot of you will probably experience in your classes, if you ever asked your students to get ready, that they do not prepare themselves. I want you to reflect for a moment on what might be the reason for students not preparing. How many of you require students to come to class prepared? Could I see a show of hands? A couple. No, more than a couple. Okay, about a third or so. So I want especially the 2/3 who did not raise their hands ask themselves why you're not doing it, or why you're afraid of doing it, or why you think your students might not come to class prepared. What is the reason for that? Actually think about it for a moment. In fact, I'm going to show, because I've asked this question many, many, many times, so I'm going to show you what the type of answers are that I've gotten. They don't have time. They're not motivated to learn. It's our fault that they do not read. We take away the incentive for them to read. 4, they don't have the requisite skills. And by the way, if I say reading, I should really change that word. I'm so used to using the word reading, but it doesn't have to be reading, right? In your case, you didn't read, you watched a video, right? So you could have, for example, your students watch a video of a lecture you gave before you switched to stopping to lecture. Think about it. From a pragmatic point of view, wouldn't that make a lot of sense? Why do we keep reenacting the same lectures over and over and over and over again? How much is coming back from the class? Questions, anyone? You've tried that, right? I mean, you stop lecturing, you ask whether there are questions, and students look down, right? There's nothing coming back. So you might as well take a camera, videotape your lecture, put it on the web, and have them look at it. Would a lot be lost? I don't think, in fact, something might have been gained, because now they can watch it when they want to watch it. Not at 8 o'clock in the morning or at 10 o'clock at night or whenever. They can do it whenever they want. They can do it not in chunks of 1 hour. They can do it in 7-minute chunks, 15-minute chunks, whatever they want. If they don't understand something, they can hit the pause button and think. Can you do that in a real lecture? No. You could raise your hand and say, Professor, I don't understand what you just said. But how many students do that? Very few. You could rewind, listen to it again. You can call up your friend and say, do you understand what Professor Mazur said at 10 minutes into that video? So I think that would make a lot of sense, right? Anyway, they don't have the requisite skills. So when I say reading, I mean watching a video, doing an assignment, going to a museum, going on a field trip, whatever, some other reason. Or 6, they come prepared to my class. So why don't you all enter what you believe to be the main reason for students failing to come to class prepared? Okay. So I'm not going to show you the distribution, but I would like you to discuss with your neighbors try to find somebody who has a different answer, right? So check with your neighbor, try to find somebody who has a different answer, and then discuss it with your neighbors. Okay, so why don't you re-answer that question in case you revised your answer, and I'd like to start a little bit more general discussion here so that we can see some of the reasoning, because it's not about the answer, it's about the reasoning, really. So please enter your answers. Okay, so let's look at the distribution here. And that's very interesting because it's changed quite dramatically. Let me show you the previous distribution. There we go. So let's see. Red is the new one, blue is the old one. So you can see that one went down significantly. Time was halved, and this one has gone up dramatically. I personally would have chosen 3. I think the culprit is us, not them. Right? There's expectations that are built up by our behavior, which is very much what you were saying, and what who else was arguing there about? You were arguing too. I mean, I remember the first time I required my students to take a look at the book before class, and I told my students, look, you can look at it after class to understand what happened in class. You can wait till 2 weeks before the exam to see if you can still cram it all in your brain and pass the exam. Or you can read it before class to prepare yourself for class. It's going to cost the same amount of time no matter when you do it. And when are you going to get the most benefit from it? If you stay on top of it and you do it proactively rather than retroactively. So I think the time argument doesn't work, right? If we put the homework before the class rather than after the class, it's still homework, of course. It doesn't have to cost more time. But anyway, I asked the students to read. I did not have the right incentive structure, which I'll talk about in just a second, right? And I'd say, oh, you know, let me just take 20 minutes to quickly summarize what was in that chapter. And what would happen was exactly what you said there. I was basically telling the students who had not read the chapter, don't worry. If you don't read the chapter, Professor Mazur will fill you in. And I was telling the students who did read, you fool, you just wasted your time, right? And the next lecture, it was 80% who did not do the reading. So we really have to start with ourselves. If you don't expect your students to read or to prepare themselves, and I'm using the word reading here loosely, I'm sorry, I keep saying read because that's what I do in my classes, but it could be watching a video, it could be going to the Khan Academy, it could be whatever you want, looking at Wikipedia, it could be doing some field work, you name it, some experiment at home, and so on. If you don't expect them to do it before class, they will not do it before class. So you got to start with yourself. On top of that, you need an incentive structure, and the incentive should not be just a stick. It should be a carrot and a stick. And that's where just-in-time teaching comes in. So just-in-time teaching, and you can find more information at that URL, www.jitt.org. And by the way, you don't need to scribble down notes. My slides are already on my website. You can download them now if you have your laptop here, but you can also just wait until the end and then look over all my slides. They're right there. On the front page, there's a link that says Recent Talks. You click on it, and then you have a copy of it. So what is JIT? JIT consists of, you know, for each topic or class meeting, you have an assignment. And again, it says reading there, but it could be anything. And then the assignment has a component that's due before class online. A couple of years ago, not all students had access to online, but I think that's changing so rapidly that all of them can find some web browser somewhere to enter their answers. The online assignment has 2 questions that are not simply questions that you can fish out of the reading or video or anything, right? So you cannot read the question, then do your assignment and say, oh, here's the answer to the assignment. No. You have to take what's in the assignment and extrapolate it to a new context. Most students, even at Harvard, cannot do that. But that's okay, because we don't expect them to learn everything from one simple assignment. Be nice, but that's not how learning works. The reason I do this is because I don't want to make it easy for them to find the answer. You say, well, that's unfair, because now I'm making them read and I'm testing them and they fail the test and punish them. No, because it's not graded on correctness. It's not rated on quality. It's rated on effort. I tell my students, you need to convince me that you have done the assignment. Well, they'll do whatever they can to put in the right words to convince you that they've done the assignment. And let me tell you, it's very easy to judge. It's much easier, actually, because you can scan it and very quickly find out whether they've actually put in the effort. This is 10% or 15% in some of my courses of the course grade. Right? And I tell my students it's just an insurance, right? You do the reading or the watching, you convey to me that you've done it, you get that 15% course credit. So that's the stick. The carrot is the last question, which is the most important one. The last question is a feedback question. I asked the student in my case, please tell me what question you have after doing this assignment. I actually tell them, please tell me what you find the most difficult topic of the things that you have been exposed to. And I have them pick one. I don't want a laundry list, okay? If they don't find anything difficult or confusing, they have to tell me what they found most interesting. Why? Because I don't want to accept as an answer everything was clear. Right? I don't want to let them get away with that. Right? So the night before class, I press on a button on my website. I get a list of the faces of the students with their names, and in 1 or 2 or 3 sentences what they found most difficult. I review that the day before class. And I base what I do in the class on this feedback. Actually, it's exactly what I did with this workshop. I had you watch this video. I had you give me feedback in the form of excellent questions, which you will see on the board. If you did your homework and you watched the video and you asked a question, they'll be there and we'll address them. Now here we unfortunately have only one cycle, but if this was, let's say, a semester-long course and you would be coming to this course every week a couple of times, you would very quickly discover that by taking this question seriously, you can influence what happens in the class. And then the next day you see that Professor Mazur is actually taking your question, or paraphrased question, and he's actually dealing with it. That's a very strong incentive, because now the instructor is there to help you as a student, rather than just basing what happens in the class on his or her imagination, which is what we typically do, right? We plan a class based on our experiences and on what we think the students need. But you know, most of our students are not like us. They have different needs. They're not going to be professors. Right? They're going to go on to other jobs. So it's likely that they have very different difficulties from our own. So that together, the stick, the credit, and the carrot, the feedback, helps. And then you keep repeating this. So what does JIT do? Prepares you as an instructor for class. It also prepares the students for class, but more importantly, it prepares you for class. The students will feed to you the questions they have. I put this workshop together based on your questions. It helps you address student difficulties rather than just, you know, lecturing in the abstract. So that's one component. That's the out-of-class component. Now the in-class component. Main features, you know, read before class. In class, it's not about covering everything. No, the covering has been done by the pre-class assignment. In class, it is about depth. Depth on the areas where the students need help. And I do that not by telling, but by questioning in the form of what I call concept test. So I get into class, I talk a few minutes, shorter than I've talked here right now. I put a question on the screen. I let the student think for a few minutes. After thinking about it, I poll them. After polling them, I look at the result. I do not show it to the students. If more than 70% is correct, I ask too simple a question. And I basically wrap the question up and repeat it. If between 30 and 70% have it correct, that's ideal. I tell them, now turn to your neighbor, find a neighbor with a different answer, and then usually the percentage will go up dramatically. I'll show you some data later. Explain, wrap up, repeat. If less than 30% have it correct, there's not enough students who know the right answer to have this right answer and the right reasoning spread. My question is too hard for the audience. So I basically wrap it up, revisit the concept, and repeat it. Of course, the ideal pathway is this one in the middle. Right? But that means matching the question difficulty to your students. We'll talk about that later. That's where the learning takes place, because here you have students, as I explained in the video that you watched. So what does it do? It helps students overcome difficulties, the difficulties that they told you they had. It encourages deep learning, because all of a sudden it's not just about the answers. So much of our assessment is about the answers. But as we all know, the crucial part is not the answer, it's the reasoning that leads to the answer. Whether you're teaching history or whether you're teaching psychology or whatever, it's a way of thinking. It's not just regurgitating facts. Especially in an information age where we can have computers regurgitate facts. Right? So no matter where you teach or what you teach, we have to go a step further. Provides depth, not just coverage. And the other thing is that when students talk to one another, as an instructor, you don't just stay there, you know, go on your cell phone or whatever. No, you walk around and you listen into the discussions. And you find out how your students reason about it. I've had so many times that I asked a question, I listened to the students talking and say, oh wow, that's how they are thinking about it. That you discover this misconception that they have that you might have had when you were a student, but you've forgotten about it. Right? Because that's the problem. The curse of knowledge, right? We become expert in our own disciplines. We forget the difficulties that a beginning learner faces. But this actually primes you again to them. When you teach each other, it's probably better to have a different person, somebody you don't know, somebody you've not interacted with, rather than somebody of a similar ability level, similar, you know, gender, race, whatever, right? It's better to mix them up. How do you control that? Well, I tell my students that they have to find somebody who gives a different answer. Right? So if you turn to your neighbor, we're going to try it out in just a second, and your neighbor has the same answer as you say, thank you very much, and you find somebody else. Then you try to convince that person. You introduce yourself first, because there's chances that you don't know everybody around you. If everybody around you has the same answer, don't just sit there. Get up and go to those people who are sitting alone in the back, who should really be sitting next to somebody. I will go and keep them company in just a second. Last warning. And keep that going. Okay, so I'm going to ask you a question. I'm a physicist, so this is sort of a, you know, general science. It's a pretty simple question, but I've done it with Harvard professors and they don't do that well. I hope you do better. The people yesterday at UDC-CC did better than my colleagues at Harvard last week. I had 300 professors at this Harvard Initiative for Learning and Teaching Symposium, including some really big names, and only 20% got it right. Okay, so thermal expansion. Materials expand when they get hotter, right? And this is particularly pronounced in metals for reasons that are irrelevant for this question I won't get into, right? So cold metal is smaller than a hotter metal. It expands. It's very important in engineering, right? Because I don't know if last time you sat in a train, but if you're in a train, you can hear this clickety-clack sound when the wheels go over gaps between the rails. And you may wonder, why do they leave gaps between the rails? Well, if they did not leave gaps between the rails, right, and the rail would expand, buckle. And if it buckles, the train derails. So they have to leave a little gap, and that's what gives that clickety-clack sound as the wheels go over these gaps. Same with steel buildings. You have to take into account the expansion, the thermal expansion of the steel. Otherwise, you know, plaster will, you know, shift and break, and you get all kinds of problems. So in engineering, this is an important problem. Now, I don't want to get to engineering and so on. I just want to tell you a little bit about thermal expansion. And the reason is that everything is made up of atoms, and in a metal, the atoms get further apart from one another when the metal heats up. So this is a cold metal, that's a hot metal. I only showed 9 atoms, either cold or hot here. You have to imagine billions of billions of billions of billions, even in a small chunk of metal, right? They all get further away from each other, all of them. The reason, and it's not that important for this question, but I'm just telling you out of interest, is that atoms don't sit still, they vibrate. And what we interpret as temperature is the amount of vibration. So this is cold atoms, and these are hot atoms. Yeah. Questions, anyone? Before I ask you a question. Yes, very good. Very good. Very perceptive question. Do you see that? Cold, hot. The center one doesn't move. What would have happened, and that's basically because I just centered these two images on each other. Imagine that we were somehow holding this atom in place, right? I'm holding this in place. What would happen to the middle one then? It would move. Which way would it move? Away from this one. So now they would all move that way. So I just happen to have chosen that the center atom remains on top of each other, but that's an arbitrary choice. The important point is that they all get further away from each other. This one from that one from that one from that. And even if I had left this one here, that would still have been true. They all get further away from each other. Yes? Question is, it doesn't matter what material? Yes, it matters. Some materials have a bigger, what is called coefficient of expansion. They expand more with a given temperature rise than others. So, for example, gold might expand. I don't know if this is true because I haven't read. I don't know the coefficients by heart. But gold might expand more than aluminum, for example. Maybe there's an engineer in the audience who knows about it. But I think that might be true. Okay. So yeah, different. So this comes back to the same question, right? You could take a metal and heat it from 100 centigrade to 200 centigrade and measure how much it expands, right? And then you have a coefficient of expansion and different. But we won't get into any of this. Okay, my question will be much simpler than that. So two more questions, you and then the person in the back there. In an earthquake? In an earthquake, does the same thing happen? No. This is really simply the expansion with temperature. You know, earthquake, I'm not a geologist, but I'd be really surprised if that had to do with any thermal effects. What's going to happen to that diameter of the hole as the metal expands? Will the hole get larger or will it get smaller? So let me start the vote. Here we go. So I'm going to give you 2 more minutes to think, and if you have answered the question, ask yourself, how am I going to use that argument of the atoms getting further away from each other to convince my neighbor that my answer is correct? No talking to each other yet, sir. You get a chance in just a second. And remember what you need to do. You need to, when I tell you, find a neighbor who has a different answer. A different answer. So if you have 1 or 2 and your neighbor has either 1 or 2 or 3, you say, thank you very much. You can find somebody with a different answer. Get up if necessary. And if you're in the back alone, be sure that you find somebody or else I'll come and talk to you. Okay, so go ahead. Find a neighbor who has a different answer and see if you can convince that neighbor. Go ahead. Talk to each other. Now look at this. Look at how you're all fired up. Hello? Look at that. They can't stop talking. Can I have your attention? Hello? It's just wonderful. Look at... They can't stop talking here. It's probably most of you have forgotten that I'm here not to talk about thermal expansion. I'm here to talk about teaching. And your conversations were no longer about the answers, but about the reasons for the answer. And it was not just one person dominating, it was everybody engaged at the same time, right? Anyway, I want you to indicate, and I know I should have given you more time, but I'm not here to teach you physics. I want you to indicate what you now believe to be the right answer. So press 1, 2, or 3, depending on what you now believe to be the right answer. And let me tell you, you did better than the Harvard professors last week. But that's only relatively speaking. The initial correct number of responses was just 23. 1 in 4. So what does that mean? That means, Eric, you suck as a lecturer. You're not good. You all thought that I gave a perfectly clear lecture, right? Right. But the misconception about what happens when atoms get further away from one another, I did not dislodge that because I didn't confront you with it. This question did. Miraculously, even though only 23% got it right, 1 in 4, the number of correct responses went up dramatically. Now, it doesn't matter what the correct answer is, because I'm not here to teach you physics. No, seriously, I'm here to teach you about pedagogy. Now imagine I just lectured you on thermal expansion. You may have taken some notes, you know, some may have been asleep, checking their phones, whatever, right? Now you're not going to let me leave this room without telling you what the right answer is, right? That level of engagement, isn't that wonderful? Isn't that exactly what we want with our students, right? Now you experience it from a student point of view. It's great from an instructor point of view too, right? Again, so the correct answer is, do you really want to know? The correct answer is answer number 1. Only, now look at that, you're all talking again. And I'm sure that you want to know why 1 is correct. All right? It's about the why. It's not about when a thermal plate expands at a circular hole and the hole gets bigger. So could we hear an explanation from somebody who had 1? Somebody who's not a physicist, preferably. Sorry, you're disqualified. But I bet you that there are a number of people who are thinking the following. There are atoms here that are trying to get away from atoms right next to it, so they expand into the hole. So this is the plate first, without a hole for now, and this is the plate after. All of them have to get further away from one another. Now think about this. Imagine you have your wedding ring and you can't get it off. Stuck. What do? Hot water. What about the hole in the ring? Gets bigger. Or think about it this way. Imagine we have a metal plate, no hole in it. You take a pen and you draw a circle on it, which I think is what this gentleman was just saying here. Now you heat this plate. What is going to happen to that circle that you've drawn? It gets bigger. But I could hear some of you argue, yes, but that's not fair, because there's no hole. If there were a hole, it could expand into the hole. Well, let's consider the atoms at the edge of the hole. Let's imagine we all go outside. It's a nice sunny day. We could do it, actually. We're not going to do it. We form a large circle. We are the atoms at the edge of the hole. There we are, big circle. Right. Now we step inwards towards the center of the circle. What happens to the distance between us? It gets smaller. Can't, because our neighbor is shaking more. Right? The only way to make the distance between us bigger is to move outward. You won't forget this. What happens here, this question was actually too hard, right? It fell below the 30% cutoff. Right? If you have a question where the correct number of answers are between 30 and 70%, it jumps up much higher. I'll show you data later on. And then the number of students who do not have the right answer is significantly reduced. Here, what was the distribution? We had we still had 70% give the wrong answer after the question, which leaves a very dissatisfied feeling, right? If you have only 20%, you have 80% who says, I get it now, and you have 20% who knows, I better look at it again. Now, this will not be a single question in isolation. I usually scaffold my questions, starting with easy and then a little bit harder, and then I come back and spiral back on the same subject. So there's going to be other opportunities for people who don't get it right the first time around to revise their thinking and working. So you really have to do a series of questions, which I'm not doing here. Look at the engagement. Your mind is still working on it. It's fantastic, right? So the point is, A, lectures don't work. My brilliantly clear lecture was useless. 2, you're engaged, which is exactly what you want with your students. Here's something that another person asked. Can this method be used in disciplines where questions might not have right or wrong answers? Suppose you teach philosophy or you teach history, right? Yes, if you ask in what year did the Civil War end in the United States, then there is only a right or wrong answer, but that's fact recall, right? But the causes of the Civil War, well, it might depend on your interpretation, and not all historians might agree. And there might not be a single correct answer. And I would have probably told you 5 years ago, I don't think this can be used outside the sciences, until I had the opportunity to teach a course on ethics, on responsible conduct in research, because the NSF now requires all universities that have government funding to train their students in responsible conduct in research. And given I was on a committee, I volunteered. I can't say the word no, so I volunteered to do it. And I thought, am I just going to tell the students about this can be done, this shouldn't be done, this is what you should do? What then? I thought, no, it's much better if I make the students think about the actions they take and the consequences of them. So I thought, I'm going to run this using peer instruction. So let me show to you a question, and I'm going to use data handling. And this is actually using an example from a paper that was published by two of my colleagues in the chemistry department. They wrote a paper about little plastic beads that are about 1/1,000,000th of a meter in diameter. So a human hair would be the width of this building on this scale. This is 1 micron. And these little plastic beads, under certain circumstances, which is irrelevant for this discussion, arrange themselves in this perfectly triangular fashion. This is what I took their microscope image, which I will show in just a second, and manipulated a little bit to get this beautiful image by doing 5 operations on it. I'm going to take the original as published illustration, and I'm going to manipulate it in front of your eyes and make it actually much more beautiful than it is now, because I love Photoshop and I'm quite good at doing Photoshop. So I'm going to do 5 steps, and at some point you may think, wait a minute, Eric, you've crossed the line here. I want you to determine when I cross the line in your eyes, right? Step 1, step 2, step 3, or if you find that everything I do is fine, you would choose 6 basically, right? Okay. And I'll show you a summary of what I do before you get to vote. Okay, notice that the contrast is not very good, right? This is the way it came out of the microscope. So the first thing I'm going to do is I'm going to enhance the contrast. There, right? It already looks better, right? Now notice that as I enhance the contrast, there are some blemishes, little dots, like dust particles, that show up. I don't know if you can see them from there. Let me zoom in so you can actually see them. There they are, right? See them? There's one there, there's one there, there's one there. Okay, I love the healing brush. So step 1 was enhancing the contrast. Here's step 2, healing brush. I'm going to erase these little blemishes, like dust, whatever they are. Isn't that fantastic? Okay, there we go. So I've removed the little blemishes now. That's step 2. Step 3 is, these things are a little bit small, and there are some problems here. There are 4 there. There's 4 there, right? So I'm going to do is I'm going to crop this image. That makes everything a little bit larger, and we can really see the point of the paper, which is to show this triangular arrangement better. So I'm going to crop this image. Here we go. There we go. So that's the next step. Cropping this image. There we go. Now let's fill the screen again. So I've cropped it. Now it's starting to look really good, right? But we still have a problem. 4, and then this has this little defect here. This one didn't quite get together well. This bead is, so you know what I'm going to do? I'm going to take this tool. So the steps are now 1, contrast, 2, remove the blemishes, 3, crop. Okay, now the next step, I'm going to remove the outliers. So I take this, and I'm going to basically remove these annoying outliers. Wait. Don't shout it out. Let everybody decide for themselves, okay? Here we go. Now look at that. Isn't that better? So now I've removed the outliers. Next step. But, you know, I've not made up anything. I've basically simply moved the little triangle from one part of the figure to the other. Okay, so now the next step, since I love Photoshop and I'm so good at it, I'm going to actually be a little bit more drastic. There we go. And, you know, take the parts of the image that are not really good. And now we have the final image. I could do it one more time maybe, but now I finally have this image here, which looks significantly better. So this is what I've done. I've adjusted the contrast. If you think this is no good, you click 1. I've removed the blemishes, cropped, removed the outliers, reconstructed the image. So basically I want you to focus on at which of those steps I violated the acceptable standards of ethics.
What is the purpose?
The purpose is to show that these things, these little beads, arrange themselves in a triangular fashion.
It's science, not art. Yeah.
This is science, it's not art. It was published, this was actually published in the journal Science, the original image. Okay, so choose, I don't want to accuse my, yes? Does the research article explain the significance of the outliers? Well, this is a hypothetical case. So, you know, imagine yourself having collected that microscope image, right? And then, you know, if you remove the outliers, you could explain in the article the significance of the outliers. It has been published, but what was published was actually the original image. I am manipulating my colleagues' data. Okay, so please select what you would have found where you find I crossed the line. Okay, so please enter your choices. Okay, did everybody make a selection? And if everything is fine, you select 6, right? 6 means this is okay, everything is okay. Okay, so let's look at what the distribution is. And notice that we have a very broad distribution, right? There's no general agreement as to where, you know, there are some people who are fine with 4, but not 5. And there are some people who think that even enhancing the contrast is no good. And lots of people in between. So find a neighbor who has selected a different step and see your rationale, check your rationale. Okay. And again, I'm sorry I'm cutting your discussion a little bit short, but notice, same level of engagement, right?
Yeah.
I don't know if there's a correct answer, and I don't even know if we will ever reach a consensus, even if I let you talk forever. Let's see what the distribution is now. Please re-enter your choices, either the same one or a different one, depending on whether or not you've revised your opinion. And you see, look at the conversation picks up again, right? People they're arguing, they're not listening to me, they're so engaged. He's not even hearing what I'm saying. They were talking about him. No, it's fine, it's fine, it's fine. It's exactly the point I want to make, right? Engagement is the same. There is no right or wrong answer. You're thinking about it. Rather than just swallowing what I'm telling you, you're forming your own opinion, which you will need to do if you were students in my class later anyway. What I do in this class is that I then show the post-discussion response. Notice that it's changed dramatically. It's shifted towards the right. People are all of a sudden more cautious about their actions. What I do in the course that I teach is I have a follow-up scenario. I say, your paper gets accepted, and the editor of Science sends you an email asking you to send in the original picture for posting on the website. What do you do? Send in the picture you doctored up, send in the one step before the last step you took, or send in the actual original. And the students go, oops, I hadn't thought about that. Right, so I try to prime them that, you know, there may be consequences to every decision you take. Anyway, I'm not here to teach you ethics or data manipulation or anything. What a point I really want to make is, you know, you got engaged even though there is no correct answer. Okay, so you can use this any discipline really. Anything where there's an interpretation or a model or anything that involves thinking. And I would argue, whatever you teach, that is the case, or it should be the case. Okay, so now let's talk about implementing JIT. How is preparing a class with peer instruction different from preparing a lecture-based class? Some of you were concerned. There was one question about somebody who was concerned about the amount of effort that is involved and that goes into it. So what do you do when you are doing a traditional course? Well, you look at the material. You may assign a book or something else, or pick a book to prepare yourself from, or a set of lecture notes you've developed before. Each time you prepare a lecture, then you deliver the lecture. You might be handing out assignment, and then you repeat that with the next topic until the end of the semester, and you have some final assessment. Okay? Here, you would prepare a reading. You would still decide, select the content of your course, but you would prepare a reading assignment, review the feedback from your class, prepare the questions to ask in class, lead a class discussion, and then pretty much the same, hand out assignment, blah, 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 and so on. So where does most of the effort go in a traditional class? It goes in preparing your lectures and delivering your lectures. Two activities I might point out that take place in isolation, disconnected from your students, disconnected from feedback from your students. You base your lectures not on what the students really need or might need, but on what you think they need. And I know from experience that no matter how much I think and hard I think and try to reconstruct my own learning, the two are often disconnected. Here, you make the reading assignment, but that's not a lot of work, right? You review the feedback. That is work. But now you're listening to the students. You prepare your questions. That's a lot of work. And then you lead a class discussion, which is a lot less work than delivering a lecture because, you're interacting. You get to know your students. It's actually fun. It is very difficult for me now to deliver a lecture because I keep thinking, what is my audience thinking? Are they with me? Have I lost them? I lose that connection to the audience. I would say, from experience, it's the same amount of time. Maybe I find this actually more onerous and harder because I have to script every second of what I'm going to do in front of the classroom. Whereas here, I just have a set of questions, and if I've prepared those questions the year before, I can ask the same questions again. So it's not the amount of time, it's the quality of the time spent in preparing. The new activities are the reading assignment and the questions for those, and the concept test. That, of course, is a key point, so we'll get back. Another question that I get asked a lot is, how do I make sure that all topics are covered? When I lectured, I covered everything. But that's not what matters. What matters is not what I cover. What matters is how much the students learn. And the test that I gave those students that I reported in on that video shows clearly that they didn't even learn what was covered in week 2. And then the whole thing unravels. So basically, I was covering everything, absolutely, but the students were learning nothing. It's not the covering that matters. It's the uncovering that matters in the brains of the students. How much do the students actually learn? Right? So yeah, you can lecture and build up this illusion, this castle in the sky, this house of cards, that you've covered everything, but in reality, nothing has been learned. Thermal expansion, I covered thermal expansion. I covered the essence of thermal expansion. You got it wrong. Few of you had questions, more than a normal audience has actually. See, a lecture actually builds up a false impression. And I'm sure you've had that. You go to a colloquium or a seminar in your own field, or you go to a conference and hear talk about your own discipline, your research. And you think, God, this is a great seminar, great colloquium. A week later, you come back home, and a colleague says, did you go to that conference? Yeah, I went there. Did you hear to the talk, the lecture of so-and-so? Yeah, it was a great talk. Really? What did he talk about? Well, and then all of a sudden you realize that you actually don't know exactly what he was talking about anymore. Right? You may have become enthusiastic, which in and of itself is a good thing. But it was not as clear. See, in a lecture, you hear things, and there's no time to assimilate the information. There's no time to realize, as a student, that what is actually, the thinking that is going in your head is actually different from the way you should be thinking about it. You don't see the difference between the two. And it reinforces this illusion that everything is clear. So I would totally agree with what you said there. You know, more is actually covered when you teach interactively or you force your students to think. And there's been interesting retention study done at Carnegie Mellon where they showed that just 2 months after taking 2 semesters of physics, the non-majors are back to where they were before taking the course. Right? So you go from September to July, they take this physics, then they just pass the exams, and you go to the next September, they answer things the same way they answered on day 1. Nothing is left. The majors do better. Why? Because it keeps being reinforced and reinforced and reinforced, and they get opportunities to be confronted with their misconceptions, but the non-majors are not. Most of the students we teach are not going to be like us. They won't have this opportunity to finally come to grips with the material. Most course design simply consists of a list of topics that needs to be covered. And then, you know, you start covering those topics, and then the assessment becomes an afterthought and usually consists of simply the students regurgitating the content back. I think a much better approach is one that's been advocated by a number of people, which is the so-called backward design. You start by thinking about the learning outcomes. What are the things that I would like my students to be able to do at the end of this course? And you use Bloom's taxonomy to basically articulate those learning outcomes. And you can check whether it's a well-articulated learning goal by asking yourself the question, how am I going to tell whether or not they can do it? Right? So if, for example, in a healthcare course, it's important that the students coming out of the course can recite a certain fact, right? Then you just say, I hope that at the end of this course, the students can recite this or that fact. But hopefully there will be also learning goals that are a little bit deeper than that, right? I would like my students to be able to recognize, you know, this or this given on these symptoms and so on, right? So basically you start by articulating these learning outcomes, then you're asking yourself, how am I going to assess those learning outcomes? Once you have satisfied yourself with having come up with an adequate number of learning outcomes, you can think, what am I going to do in the course in order to achieve those learning outcomes? But as long as we're wedded to content, it's going to be very difficult to have meaningful learning outcomes. So I think a very good exercise that I've started to do in the past 5 years, and which is not easy, I don't want to make this appear simple and easy, is to revise my syllabus and force myself to articulate more meaningful learning outcomes than simply say, in this course we're going to cover topic A, topic B, topic C, topic D. My first attempt was, after completing this course, the students will be able to understand topic A, topic B, topic C. I mean, that's clearly was my beginner's attempt at formulating learning outcomes, and then I realized that's not a good learning outcome. I really have to have something a little bit more meaningful. Now, there's a problem, because in some cases our students need to pass standardized assessments that are outside of our control. The MCATs, maybe some kind of a nursing exam, whatever. If those assessments don't have clearly articulated learning goals and are simply fact recall, then you got your hands tied, right? Because then, yeah, the student will have to use flashcards and, you know, memorize information, which is totally ridiculous, because when they are actually practitioners, they can grab their iPhone, press the button and tell Siri, you know, give me this fact, and it'll spew it back. We'll talk more about assessment in just a second. So I agree, if you're leading up to a standardized assessment instrument that is poorly designed, You got your hands tied. But still, I would say having you recite the information for the student is not going to be what is going to make them memorize it. So you might as well make good use of the time. My students, pre-meds, many, have to pass the MCAT exam, right, in order to get into medical school. It used to be that the MCAT was a really poor test. It's getting much better, much more about thinking and about outcomes and about skills than about memorizing facts. But my students told me that after taking my course, simply because they understood the physics better, the physics part of the MCAT was actually the easiest part for them, which was not something that I heard when I taught a traditional test. So simply the better way of thinking reinforced the retention of information. And if you want to learn more about the contrast between retention and misconceptions, there's a talk on YouTube, which is in parts, which is called Visualizations and Visual Illusions, How the Mind Tricks Us, which I gave, where I confront, I show how presenting things can sometimes rub in the wrong way of thinking rather than unseat it. Students have expectations just like we have expectations, right? But don't forget that I'm basically taking the homework, which normally comes after the course, and put it in front, after the class, pardon me, not the course, and I put it in front of the class. So I make the homework that comes after the class less than the ones that I used to make, right? So I'm basically shifting things. I'm flipping it. How do I get examples of good questions? Imagine that I have, at the end of this workshop, and we're not there yet, I see many of you still sort of, resisting this idea. And, of course, you should resist it. After all, we're all products of this old system. That is and we tend to project our own experiences onto the world around us. But that is because we forget how we learn. Remember that first question I asked you at the beginning, right, about how we learn. You all admitted that whatever skill it was that you wrote down that was important in your career, that you did not learn it in a lecture. You learn it by practicing, right? Yet, we all attribute our successes to our education and to the diploma that we got from our universities. I would argue, actually, and I'm a little bit on a tangent here, I would argue that when we hand our diplomas to our students, whether it's a bachelor's or a master's or whatever, or an associate's degree, PhD, that's not when the learning stops. That's when the learning really starts. I have probably forgotten, and I'm not ashamed of admitting this in front of you on camera, you can post this on the web, I have forgotten 95% of everything that was ever taught. And I would be really surprised and impressed if you had done any better than I did. I learned history as a simple collection of facts. The British, I was educated in Europe, so we didn't learn US history, we learned European. The Dutch defeated the British in the River Thames in 16, I'm ashamed to say I forgot the year, but on exams I just had to regurgitate that date. I did well enough to get into university and to succeed in my career. Did I understand better what the historical context was that led to these events? No. Right? And I forgot. And I forgot chemistry, and I forgot probably most of what it is. In fact, I forgot the faces of some of my teachers. Yeah, I remember some, but I remember that I have no idea who they were. So the real learning doesn't take place in formal education. What is more, when we give our diplomas to our students, they're on their own. They're not going to learn the skills in a formal environment like they did before. And the same was true for you. Most of the things you've learned were on the job, not in a structured way. So I think one of the most important skills is to learn how to learn. Isn't that what JIT and peer instruction actually do? They teach you, in addition to helping you uncover difficulties, they teach you as a student how to learn. How to gather information that's available, process it, start to make sense of it, then talk to your peers to make more sense of it, and so on. Anyway, how do I get examples of good questions? So I'm not sure you're there yet, but that's okay. Well, First is to look at what's available. There's a book with physics questions, with chemistry questions, with astronomy questions, with calculus questions. I never had an idea. I was simply trying back in 91 to solve a problem in my own class. I never imagined I'd be, 20 years later, I'd be talking in Washington to you about this, and that books would have been published about it, articles about it. I'm totally surprised. I was simply trying to solve a problem in my class. I wasn't trying to invent peer instruction or anything. But as you can see, there are lots of books. And you'd be surprised what happens if you do the following Google searches. Type in your discipline, healthcare or nursing or philosophy or whatever, and then the word concept test. Or your discipline, whatever it is, open quotation mark, concept, space, test, quotation mark. You need these quotation marks, otherwise it looks for the word concept and test separately, right? So this, and unfortunately I spelled it this way specifically so that you could easily search for it, but some people don't follow that hint, and if you type it this way you'll find too many to be. And the same with peer instruction, but you have to put the quotation marks. You'll find pages on people applying the method in the humanities, in philosophy, in veterinary medicine. I mean, things I could not have imagined, including questions ready for you to use. Or you could write to the instructor and ask, hey, can you share your questions with me? So what are the important parts of a concept test? So you need an intro. In my case, it was the little lecture on thermal expansion. You need the question, so that sets the context. You need the question, which was the hole in the plate, right? You give students time to reflect individually on the answer, poll them to get baseline data. Then there's the learning that takes place in this peer discussion. You poll them again to see how things have improved, the second polling. I do not show this to the students, right? You did not see that distribution. Why? I did not show that initial distribution because, as I told you, I want the number of correct answers to be above 30%, somewhere between 30 and 70%, right? So if with 5 choices you want it to be above 30 or 70%, that means that the majority answer should initially be the right one. If I show you the distribution and you see the majority answer, you tend to congregate on the majority answer. People are, somebody said before, people are like sheep. It's even worse when you show data, right? They follow the data. So I don't want that baseline data to influence the discussion. And then you wrap up to provide closure. How long does this take? Well, about 5 minutes for this, a few minutes for these parts, 2 to 3 minutes here, a few minutes for closure. So you see, you're still talking 10 minutes, but the whole thing takes about 15 minutes. Can you save time? Yeah, you could omit. There are some people who try to save time by cutting edges here. For example, you could poll them and then immediately wrap up. But now you've taken the peer out of peer instruction, right? It's like the rock, giraffe, and flower question, right? There's no learning. There's no confrontation with any misconceptions. You just go on. So I think this is a bad idea. The other possibility is just to launch straight into the discussion. And I always felt queasy about that because I thought, you know, I would like people to commit to an answer before they talk so they have time to think about it. I never did the experiment, but a group in Glasgow did the experiment and published these findings in this paper here, the Studies in Higher Education, about 7 years ago, 2003. They did 2 classes, one where they launched straight into the discussion, and another one where they had students, they polled students, no, they gave students time to think, and then they polled them before discussion. And they found 2 things. Those who had thought before discussing and then been polled before did better than the students who launched straight into the discussion. Also, there was more satisfaction. Students complained, right? Imagine you're here, you're thinking, you see the question, and before you have time to think about it, your neighbor starts talking to you, right? It's hard to participate in a meaningful discussion. So even though you save 1 to 2 minutes, I don't think this is really good because you don't have any information about the effectiveness of your question either. You don't know if this discussion has been meaningful because you have no baseline data. So that means you really need to spend about 15 minutes per concept test. Diversity is absolutely essential. If you had a homogeneous class, peer instruction would not work, right? And you say, well, you come from this elite school, Harvard, where you get top 1.5%. You'd be surprised at the diversity that there still is at Harvard, because the admissions office pushes very hard. We have people from all over the country. I have students from Tanzania in my classroom, from Asia, from all over the world, very different, Middle East, you name it. People who have very different educational experiences before they come into Harvard. Yes, they've distinguished themselves in some way, but the diversity is absolutely remarkable. But what happens, imagine that, Bev and I are sitting next to each other. She's really, very smart, good. She knows the answer. She understands everything. I don't. I learn from Bev. But likewise, she learns by the process of explaining it to me. Because, as you know, who's the person who learns the most in any classroom? It's the teacher. I have sometimes taken on the teaching of a course because I wanted to learn the subject. Right? So what happens is not that I'm learning at the expense of Beverly. No, we're both moving up. Right? So that diversity is important because that permits you to have an environment where some students become the teachers, and it's not always the same students. On some subjects, some students are the teachers. On other subjects, another students are the teacher. And everybody benefits. And you have all this parallel processing going on. It's not just one person teaching many. No, it's a lot of teaching, a lot of people teaching a lot of people. It's actually not that different from the case study method. Peer instruction, if you stop to think about it, it's an old thing, right? Well, it's actually very old because Socrates already told us 2,000 some years ago we should teach by questioning and not by telling. Here we're in the 21st century, we're still mostly teaching by telling. But lawyers, people teaching management in business schools realized over 100 years ago that, yeah, you could just read the law to the students, but what is much more important is to understand the practice of the law and to practice the law in the classroom, especially since in the United States, right around the turn of the century, students came from other states to Harvard, and it was no longer possible to teach the law because the law in Virginia was different from the law in Massachusetts and so on. So they developed the case study method, which focused on the practice of the law rather than on the law. Right. But in the case study method, it's the instructor picking one student and then another student and another student, and a discussion that is not as efficient, I would say, as in peer instruction, where everybody talks to everybody at the same time. Right? But the idea is much older than 20 years. Let me go on. Let me defer questions to either this afternoon or after my talk, because otherwise I can't get through the last few slides I had. Do I need clickers? No. You can do it with flashcards and have everybody raise cards at the same time. I was going to do a question with you to make you notice that there's no difference without clickers as with clickers, but we don't have time for that. I was going to ask you a simple, algebra question. And then basically I would have told you not to use the clickers, but to put your hand on your chest. So you would have thought about the question, and then I would have shown you 5 answers, and you would have done 1, 2, 3, 4, 5. At the count of 3, everybody, show the choice. If you don't, I come to you and I put the microphone in your face, and you got to tell everybody what your choice is. I'm just kidding, But that works beautifully. I've done it with audiences of hundreds. You can see the distribution. You might not be able to see exactly everybody at the back, but you can get a good sense of the distribution. Students don't see. Right? You can see you can see it like this, but you can't see it when I'm like that. Right? So as an instructor, you see the distribution. They don't. Then you have them talk to each other. Same level of engagement, because they've committed to an answer. Now they want to defend that answer. Right? So it's not the technology that matters. It's the pedagogy that matters. This was the question. I'm just going to go on. Right? It's not the technology, but it's the pedagogy that matters. However, clickers do offer advantages. One, you get data. And with the data, you can determine whether your question was effective or not. Yeah, you can sort of see it with your fingers, but you know, how much of us take data in the classroom? You don't have time to really do that. But with the clicker questions, you could later analyze the data and say, oh, this question produced a huge gain. And this question did not produce a very good gain. The other thing is you can track individual students. So when a student comes to your office, you could quickly see, how does this student do on my clicker? Oh boy, he or she got all of the questions on this subject wrong. Right? So you can track what individual students do, which are non-negligible advantages. But if you want to use it and you don't have the time or energy or logistical support or budget to invest, you can already get started without them. It's not the technology, it's the pedagogy. So much money gets invested in technology that is useless. Smart boards, this, that, and the other. We need smart students, not smart boards. And you know, I don't know why a smart board would get the information into the brains of the students faster than anything else. Blackboard, for that matter. Okay, so what happens if the students expect a lecture and are neither prepared for nor receptive to the new approach? A mismatch of expectations. I hope the person who asked this question is in here, because it was actually tagged as a UDC question. Well, you know, my colleague, Phil Sadler at the Smithsonian, has a beautiful anecdote. He says, suppose you're coaching somebody to play tennis. You're a tennis coach, right? And there's this one girl who's taking tennis lessons with you, and at one point you discover she's not holding her racket correctly. She has her thumb around the handle, and you want her to hold the tennis racket like that, with the thumb aligned with the handle. So you go over to her and says, look, you should hold your racket like this. She changes her grip. And because she's not used to holding her racket like that, all of the balls go in the net or out. And she gets upset. Why don't you let me hold the racket the way I used to? I was playing better before. As a coach, you know that if she keeps holding her racket like that, she'll never improve. So you tell her, wait 2 weeks and you'll see, you'll play better than you did before. Now, that's one thing to do when you're coaching somebody playing tennis. If you have 100 students and they all get, because of a mismatch of expectations, they get unhappy, that's really intimidating. I have some students who come to Harvard. They've been the valedictorian. In fact, almost all of them have been valedictorians in their classes. They got a 5 on AP Advanced Placement Physics C and AP Physics B and C. Right? And they come to my class and I ask these questions and they get the questions wrong. Why? Because they've been doing very well at the old system. Right? And now I'm asking them questions where they have to think, and there are holes in their thinking. What happens? Are the student thinking, I'm not as good as I thought I was? No, that student is going to think there's something wrong with Professor Mazur. And they're going to come to me, and in fact that happens. Some students will come to me and say, Professor Mazur, when are we going to do some real physics? Because to them, real physics is not thinking about holes in plates, it's simply, you know, reciting the information I've given them or solving the problems that I solve for them. A little while ago, I was at a university, a respected university south of Boston, let's put it that way. And I gave a talk, the Confessions of a Converted Lecturer, and after my talk, a professor came to me and he explained, he was a physicist, and he told me how we had worked really hard to put physics in the context of the real world. And the context he had used was baseball. Everything was baseball. There's a lot of physics in baseball, right? Runners running, trajectories of balls, collisions between bats and balls, and so on. And on the homework and the midterm examinations, baseball problems. By the time he got to the final, he'd run out of baseball problems. Yeah. So he put some football problems. Professor, complained to students, we've never done any football problems. And I'm sure you've had that. Students who complain that they've never done a problem of that type. Well, as I said earlier, if you had done a problem of that type, it would no longer be a problem. We want our students to, I want my students, but I'm pretty sure you want the same thing. I want my students to stand on my shoulders. Not simply to regurgitate the things I deliver to them, not simply solve the problems I have solved or somebody else has solved. I want my students to solve the problems that have not yet been solved. Right? And I think we all want that. Well, if you never give them the opportunity to do that in class, they're going to complain when you do it, and they're never really going to be able to go beyond regurgitation and rote memorization, which I think is a real problem. Well, I spent quite a bit of time, this question came up several times in the break too, I spent quite a bit of time trying to motivate my students. I tell them, you know, how meaningless it is to lecture. Still, I have some students who complain. I want to show you some of the vitriolic emails I get. This is from a student 2 weeks into the course. Subject, concerns. Imagine, you know, you're watching your email come in and you see the name of a student and it says concerns. You know, your heart already starts beating faster. Professor Mazur, here are a few concerns. I speak for many of my classmates. 1, you're giving us way too much work. After spending multiple hours on the problem set and not being able to figure out many of the questions, I now see that we have an additional 6 or 7 pages of homework in the workbook. I just spent 4 hours on the lab and I'm not confident on almost half the questions. This is more work than I've had all semester in all of my other classes combined. 2, if you are going to give us this much work, I would suggest restructuring the lectures. Here's a student telling me what to do in the classroom. Right? I find the readings very difficult to understand. I'm not a bad student. I got a solid A in Physics 1A, which was the previous semester's course. But it is very difficult to internalize the readings. You should, here's a student telling me what I should do, you should spend most of the lecture going over point by point the readings in their entirety. While the clickers are fun, they do not help me understand the complex material. I'm extremely flustered by the incredibly large amount of work and my inability to understand it, and I'm strongly considering dropping the course. I had to cool down after reading that message. I waited probably a few hours. You know, my heart was beating faster. And then I decided to ask the student to come to my office. And I said, he came. And I told him, look, I love lecturing. But I can show you data that it's not very effective. And I showed him the data. He was very skeptical. And I said, look, if you want, you can come every week to my office. I have this beautiful board in the office, and I'll copy the textbook onto the board, and you can copy it from the board into your notes. He looked at me and got this sort of smile on his face. To my relief, he did not take me up on this offer. But he clearly walked away still very skeptical. Now what happened was that, and I think it was in part also because he expected that the simple reading would bring him to understanding, right? The mental block was he had too high expectations of how much he was supposed to do before coming to class. And I'd explained to him that. But what happened was that 2 weeks later, he had climbed on board. His answers became really, really sharp. And it was clear that he had changed his approach to studying and thinking. And on the day of the final exam, I got this message from that very same student. Subject, thanks. Professor Mazur, first of all, I want to thank you for a great semester. You're an excellent professor, and it is clear that you truly care about each and every student. The exam went well today. I'm not sure to what extent you will curve the final grades, if at all, but it looks like I may be right around the cutoff between an A and an A-. I studied as hard as I could, and I'm keeping my fingers crossed about the A. But no matter what happens with my grade, you should know that you're one of the best professors I've ever had at Harvard. Not only did he have an A, he had the absolute highest grade in the course. I was so impressed by his exam, by the thought he had put into everything, that I thought, this guy should not be a doctor, he should be a physicist. I invited him to come to my office, and I said, are you sure you do not want to become... I'd become good friends with him by then because, he had invited me to a student faculty dinner. He had totally come on board. And he had come, so one of us, right? I wanted him to become a physicist. Well, he had his mindset on becoming a doctor. He's now a surgeon in New York. We're still in touch. But it was clear that, the thinking was something of an important skill to him that he developed. And there are a couple of examples like that I can give you. So, you know, that initial adjustment is hard. There will be resistance. Change is difficult. There will be resistance from your students. There will be resistance from your colleagues. You're supposed to teach. You're not supposed to lead a discussion. Right? That's the expectation. Unless deep down in your heart you believe in the need for change and in the ability to change, it's going to be very difficult. So you have to be prepared for an initial period of adjustment, an initial period of some friction. And, you know, fortunately, I think the data, and this is why gathering data is so important. I hammer on that fact in Confessions of a Converted Lecturer. Get data so that when you get a colleague who comes to you, you can say, I can lecture, but this is the result. Is that what you want me to do? Right? That's very hard to refute. Okay, so quickly, what is the best way to create concept tests? Now, I may have, this is always the danger with giving a workshop. I've been at this for 20 years. When I first started doing peer instruction, there were no clickers. There were no concept tests. There was no JIT, nothing. I just started to ask questions in the blind. My questions were not optimal. Yet, it doubled the learning gain, because those are the data I showed to you in the workshop. So in the video, I don't want you to walk out of here thinking, boy, this is complicated. JIT, PI, learning goals, clickers, this, that, and the other. You can make this very simple and just start by asking some questions in the classroom without clickers, not worrying about optimally designed questions. And already, simply by the fact of engaging the student's mind, I promise you, you will see learning gains, okay? So don't be overwhelmed by everything I present today. Just try it out, and you'll see the effect that it has. So how do you select which concepts to evaluate? Well, in the beginning, I was doing that blindly, right? Just looking for material. You might be able to take inspiration from what other instructors in your field have done. I cannot help you in your discipline. I'm a physicist. But there's plenty of other people who've tried it, thousands of people. Incidentally, we're developing a social network. I'll get to that information in just a second. But the thing to do is later on, you may want to actually poll the students. Let the students suggest what the areas of the question should be. That's an incentive for the students to actually do some preparatory work. Okay, so how do you make sure they're not too easy or too hard? In the beginning, that's difficult. This is not something that you can, without ever having tried, do it right away, right? I know that the question of the hole in the plate is on the hard side. I could have asked an easier question, but I wanted to make another point, namely that the lecture is not efficient. It's not efficient not only at transferring information, it's not efficient at the audience diagnosing their own misconceptions, right? So that's why I chose a non-optimal question as a test. There was a good reason for it. But when you teach a class for the first time, you don't know which ones are too hard or too easy. Let's get an example of a question here. We put here the percentage correct before discussion versus the correct percentage after discussion. So this data point was 61% before, almost 95% after, a pretty big gain. The question that we did had 23% initially, and after discussion, what was it? 30-some, right? So it would have been here, right? If you do a whole semester's worth of questions, that's where they lie. Notice that most of them are above, right? Simply because people move each other in the right direction on average. Some outliers, but you know we can retouch those in Photoshop, so that's no problem. I'm kidding. I'm kidding. Those usually are questions that are ambiguous. Right? Because I find out, oh God, I forgot to articulate this assumption. Right? But notice that if you take all of the data together, there's a trend, and the gain is the highest here in the middle, as you would expect. So I tend to eliminate these questions. I eliminate these because these are, or I reformulate those questions, and I eliminate those. But that takes time, right? That takes time. And then you'll hit this pathway. Do you know of any networks of users who share questions? Yes. We just started a social network where people can share, find each other. We're still in the stage of just harvesting feedback. In fact, I have a number of cards here. We'll give you each a card so you don't have to write that down. Okay. I would like to see a real class, because you haven't seen. Well, there are a number of people here on campus who are apparently using peer instruction, so maybe that somebody can facilitate class observations. But if that's not feasible, I'm happy to send Bev 1 or 2 copies of my video, interactive teaching, which has a full class where you can see me in action. Before we end in 10 minutes, assessment, because I think this is an important point, right? Because what we do in the classroom is driven, and the student's behavior is driven by assessment, right? In other words, if you have an assessment that requires memorization, the students will memorize. If you ask the students to memorize the yellow pages, they'll happily do that, right? So one of the things that I have done, which I briefly want to discuss, is that, and I didn't do this in one step, I went really step by step, is that now I tell my students, because I do not want them to memorize, I tell my students, you can bring whatever you want to the exam. Well, you cannot, if you know your uncle is a nuclear physicist, you cannot bring that uncle. But other than that, you can bring, and he cannot take the exam for you, but you can bring whatever you want. Books, notes, computer, iPhone, everything. Why? Because in this age, in this information age, it's not about memorizing information and regurgitating the information. Yes, it used to be that way because, you know, suppose I'm a physicist and I don't know the mass of the electron. I've got a problem. I can't afford to run to the library each time I need the mass of the electron. But now, it's no problem. I need to know the mass of the electron. Press Siri. What is the mass of the electron? And, you know, a few seconds later, if Wolfram helps me, what is the mass of the electron? Checking my sources. Checking my sources.
This might answer your question.
And there it is. This might answer your question. And it's here in 1, 2, 3, 4, 5, 6, 7 significant digits. There's no way I could remember it with this accuracy. Right? And if I need it 10 times in a row during a week, I will remember it. I will remember it not because I crammed the information. I remember it because I used the information. I think it's important that that happens in learning in general, right? I mean, I mentioned the examples before of tying your shoelaces and putting your fork in your mouth. Well, those were not, you didn't study for an exam for that, right? It just happened because you did it over and over again and you learned the right way to do it. I think that the information that we really need in our lives, we'll memorize it because we need it and use it, not because we cram for it. And also, when I do my work as a physicist, and this is true for all of you too, when I do my work as a physicist, and I write a paper, let's say, on some of the new results that I have in my field, there's nobody standing next to me saying, "Ah, you're not allowed to look at that paper from your colleague at Yale, you should have known that." No, I can look it up. And I should even look it up. It's not about remembering the information. It's about knowing how to use the information, how to vet the information. Is it good quality information? Is it bad quality information? Those are the skills that we need. So now I tell my students, you can bring whatever you want. That has 2 effects. The first effect is I'm telling my students memorization is useless. It's about using the information. Yeah, they'll discover that they'll still need to know some information because you can't look up everything. It's going to take too much time, right? So you still need to know the basics. But it's not just about cramming flashcards, memorization, and then forgetting. There's very interesting results by Ruddy Rödinger at Washington University in St. Louis, a psychologist, who shows that you cram for information, you forget it in 2 weeks. You have it just long enough in your brain to pass the exam, and then it's gone. Gone, 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 gone. Science, Nature, several very interesting papers that you might want to read. The other effect that it had is on me. Because now, all of a sudden, if I look at my old exams and I ask myself, would this be a good exam if they had the book and their cell phones and their computers? The answer is 80% of the question I used to ask are worthless, because it's just a matter of looking it up. It's not an important skill, right? So I had to revise my assessment. I had to write much more meaningful exams. And I think that the learning that has resulted from this shift is significant. What about collaborative exams? I was at the University of Delaware a year and a half ago as Phi Beta Kappa visiting scholar. And I sat in on the collaborative exam there. It was fantastic. It was a biochemistry course on hemoglobin. I don't know much about hemoglobin. It was taught in a studio setting, tables of 8. There were 40 students in the class, so there were 5 tables of 8. I happened to be visiting one day on the day of an exam. What happened was the instructor distributed the exam to the students, and they each had 20 minutes to think about the exam individually. It was a multiple choice exam, horror, because it's really difficult to design good multiple choice questions. And I thought, uh-oh, this is not at all something I like. Students recorded their individual answers. Why is a multiple choice exam so hard to design? Because as an instructor, you know the right answer, but you don't know what plausible wrong answers are. You've learned it. You see it the right way. You have no idea how a beginning learner thinks about it. But anyway, students wrote out, bear with me for just a second. Then after 20 minutes, he collected the individual responses. 50% of the grade for that exam was the individual responses. Then he put on each table a scratch card, you know, like the lottery cards. It had on the vertical 1, 2, 3, 4, 5, 6, 7, the number of the question. On the horizontal, it had A, B, C, D, E. And at the intersections, there were the same paint that you have on a lottery card. The students but there was only 1 card per table of 8. The students had to scratch off that thing that corresponded to the right answer. So now they can talk, and they all go. Question 2 was really easy. I had C. Did you? And everybody has C. They scratch off the C, and then if you scratch off the right one, there's a check mark. If you check off the wrong one, there's a cross. It's pre-coded, right? And you could see that one student scratched it. Everybody agrees, scratch. Yeah, we got it right. Right? Okay, let's go to question number 3. Right? So first they did the easy questions, but then they had a question where half of them had B and half of them had C. You can't scratch both off, right? So which are you going to scratch off? Well, I think it's C because, no, it should be B, don't you remember? And they had this scientific discussion about hemoglobin. All of a sudden, it was no longer about the answer, but about the reasons for the answer. And they would talk for a while and then reach a consensus. Okay, let's scratch off C. They scratch off C. Oh, wrong one. Well, if you scratch the right one off the first time, you get 4 points. If you miss it, you can still get 2 points for the next scratch off. If you miss that, you can still get 1 point for the next one. After that, you get nothing, but you know what the right answer is, right? Which is great, because you walk out of the exam knowing what the right answer is. All of a sudden, the assessment turns into a learning opportunity. How many of our exams are learning opportunities? Normally, you know, you hand in an exam, right? You talk maybe a few minutes to your classmates, and then you go to somewhere else and you forget about the exam. 2 weeks later, you get the exam back. Your mind is no longer at all on the exam. You get a grade, which usually drops out of the clear sky, and you know, there's no opportunity to learn from the mistakes you make. Here, on the spot, they learn. They learn and they know their grades. Because the other 50% of the course grade is determined by the collaborative grade. So each individual in that group must participate in order to earn the maximum from that part of it. I think it's a brilliant idea. I would like to be able to do it without multiple choice. I don't know exactly how to implement that. I just want to tell you. Why do I think this is important? Because this is how we work. Whether you're a nurse, or a doctor, or a veterinary doctor, or a surgeon, or a physicist, or a historian, we work open book. This is how life is. We work with other people. Why do we assess in this artificial environment, saying you can sit here, you can sit there, one space in between, right? Now put your books away, your notes away, everything. You're not allowed to communicate with anybody. An environment we're never going to encounter in the rest of our lives at all anymore, right? If you think about it rationally, it's crazy. There's a rationale for it. The rationale is that we used to live in an age where information was in libraries, we were isolated from it. But now in the information age, that's no longer true. We better adapt or we'll have a problem because we don't teach our students the right skills. How do you assess students of different abilities and keep them all motivated? We sort of addressed that question. There was somebody who asked about, so I think we sort of addressed this. So what I would like to do is end by redoing this survey that we did at the beginning. So if you would be so kind as to take your clickers and let me erase this question because that's left over from before. If you vote now, I just opened it. Lecturing is the best way for me to cover the amount of material I need to cover in my course. I told you, notice by the way that this workshop follows the principles that I have advocated here, right? There was the pre-workshop assignment. I shaped the workshop based on your input. It was taught interactively. And now what I'm basically doing is I'm trying to assess the effectiveness of my own workshop. I gave a survey at the beginning, give another survey now. Tonight I'll analyze those data and say, I've not really reached that objective very well. Next time that I give this workshop, I better improve this or that. Okay, so let's see what the distribution is. And I think we have a shift, definitely, towards strongly disagree, which is good. Next question, interactive teaching requires significantly more instructor preparation time than traditional lecture. I think to honestly answer this question, you've got to try it out, but let's see if there's been a change in perception. There we are. Wow, that's a flat distribution. So try it out and then let me know. Next question, interactive teaching requires clickers. Okay, well, that one hit the spot. That's good. Next one, I know how to get my students to do their reading before class. There we go. That's great. We've got to shift it down there, so I'm happy to see that. Next one, it's difficult to see how to apply interactive teaching in my own discipline, in the humanities and the social sciences in particular. Okay, good. People see how they could apply it. And then lastly, I'm worried that interactive teaching will negatively affect my end of course evaluation. You already were on the strongly disagree side. I don't expect too much of a shift here. Okay, well, wow, look at that. Fantastic. I think you're all ready to experiment in your classes, with which I wish you a lot of success and luck. And I really want to stay in touch. I think it's very important. Change is difficult. What I told you today is as old as the ancient Greek. Socrates. I mean, there have been many great people in education, from, Piaget to physicists to chemists to psychologists who have argued. I've told you nothing new. I think the only thing that's different now from thousands of years ago or even 100 years ago is that something really significant has happened, and that is the sharing of information, the fluidity of information. Information is no longer a static body of knowledge. It's evolving continuously and much more rapidly because it's not entrusted to paper. It's entrusted digitally and shared all across the globe. So I think that is perhaps the biggest driver of change. But still, change is really difficult. So if you want to change, let's keep in touch and help each other, convince the others, and spread the message and get this to take hold. So thank you so much for your attention.